Welcome back, everybody. Over the past 15 weeks, we've learned several different statistical tests. And what I want to do in this video is provide you with some additional strategies for determining when each test is most appropriate to conduct. Let's start off by talking about decision trees. I think decision trees are most useful when you're studying, just to help you organize your thoughts. Let me take you through an example. This one right over here is based on descriptive statistics. Let's say I have all of your exam scores and I compute a mean, and I want to determine what's the most appropriate measurement of variability to go along with that mean. So I'm trying to summarize an entire distribution, and specifically I want a measurement of variability. Here I'm now being asked, what measurement am I using to talk about the center of the distribution? In other words, what measure of central tendency have I decided is best? And I already computed a mean. Right here it's now telling me you should then compute a standard deviation. And we learned in the past that standard deviations and means go hand in hand. Here's another one. This one is specifically geared for inferential statistical tests. Let's just go through a quick example. Let's say that I have some data from two different groups, and I'm trying to determine what's the most appropriate statistical test. It starts off by asking me what type of data I have. Is my data qualitative, which we would typically call categorical, or is my data quantitative, which we have often called measurement data? And let's say I do have measurement data. I have data, let's say exam scores, and I'm trying to compare men versus women. At this point, it asks me, what kind of question are you trying to answer? Are you looking for relationships between the variables, or are you looking for differences between groups? And I'm clearly looking for differences between the groups. Now it's asking me, how many groups do you have? Do you have two groups or multiple groups? I just have two groups. Well, what's the relationship between the two groups? Are they dependent or independent? And if I'm comparing males to females, they're clearly independent, two completely separate groups. Well, now it's telling me I should do an independent samples t-test. You will notice in this particular decision tree, there are some tests that we didn't learn. These are mostly non-parametric tests. If you come across a test that we didn't learn, like the Mann-Whitney-U, or the Wilcoxon, or the Friedman test, or the Kruskal-Wallis test, just ignore it. No big deal. What I wanted to spend the rest of our time doing was looking at some examples that we've encountered before, but examples that don't have information specifically telling you which test to conduct. And I want to provide you with some strategies for determining which is the most appropriate test. So for example, a medical researcher believes that crack babies tend to be lighter than normal healthy babies. Regarding the weight of healthy babies at birth, assume that the population mean equals 8 pounds and the standard deviation equals 2 pounds. The researcher finds that a random sample of 30 crack babies has a mean weight of 6.5 pounds. Test with an alpha of 0.01 two-tailed. So at this point, you need to determine what's the most appropriate test. What you should do first is underline, highlight some important information. So one of the first things that I want to figure out is, how many groups did I collect data from? Did the researchers collect data from just one sample, or from two samples, or maybe 3 or more samples? That's a really important piece of information. So that's one of the key things that I'm looking for first. And you can see right here, it says a researcher finds that a random sample of 30 crack babies. So that's one sample. So maybe somewhere off to the side over here, you might write down one sample. And we can verify that here. I see one sample mean. Now, what I consider one of the most important tools that you have is your formula sheet. I made a formula sheet available in this week's folder for you to print. You should have that available right next to you right now. So let's just look at the formula sheet. Remember, the formula sheet begins with just some basic formulas for descriptive statistics, means, variance, standard deviation, and then we start getting to information about hypothesis testing. So these are the different tests that we've learned. Now, you might not always remember the formal names that we've used to describe these tests, but you can look at the formulas and understand what they're doing. This is the one sample z-test that we learned. And it's called a one sample z-test because we collect data from one sample. We see one x bar, one sample mean right there. So in the situation we just talked about, this might be the most appropriate test because it's a test that's appropriate when we have one sample mean. You might recall that we also learned about the one sample t-test. This t-test is almost identical to the z-test in that we collect data from one sample mean. We have data here from one sample. So in the example research study that we just read about, this might be the most appropriate test to do. We're going to have to determine between these two at the very least. Let's go back to our example. In the example, we have information about the sample mean. We also know the population mean that we're going to compare it to. And we also know a population standard deviation. So here's the second key piece of advice. We want to highlight what's the information that's really given to us that's important. And knowing a population standard deviation, that's pretty important. Knowing a population mean, that's pretty important. Let's compare the information that we have to the formulas. In this particular formula, in order to compute it, I need to know a sample mean, and we had that information. The children who were born addicted to crack, they weighed on average 6.5 pounds. We know the population mean we're comparing it to. Normal, healthy children weigh 8 pounds. Here we need to know the standard error of the mean. Let's look at the formula for that. In order to compute the standard error of the mean, we need to know the sample size. We know that. We know how many babies they measured. And we also need to know sigma, the population standard deviation. Do you see how that example fits this particular test perfectly? We have all of the information to compute this test. So don't overthink it, my friends. If you have all the information to compute this test, it's a match. It fits. So when we come back to this example, I see the most appropriate test is to do the one sample z-test. So I want to go through a few more of these examples and just help you pull out the key information to determine, always, correctly, every time, what's the most appropriate statistical test. Now remember, sometimes I give you a lot of summary information, sometimes I give you raw data. Either way, we should be able to figure it out. Sometimes there is some key piece of information to help us determine what test to do. And all you should have to do is glance at the information right here and know what test to do. You might recall this example. We were putting students either in a cold room, a comfortable room, or a hot room, and then we were testing to see how much information they could learn. The key piece of information that's standing out at me is that I have 3 different groups, and there is only one test that we learned that will compare 3 different groups. Even when I look at some of the statistical information underneath, I can see there are 3 different sample means. Just by looking at the groups of data, I know I could compute 3 different sample means. So let's go ahead and look at our formula sheet, and let's try to remind ourselves which would be the most appropriate statistical test when I'm trying to compare 3 different groups. This particular test right here focuses specifically on one sample mean, and so does this one. So those tests aren't going to work. This is an independent samples t-test. It compares 2 different sample means. We have 3 different groups that we're comparing. The independent samples t-test isn't going to work. The related samples t-test isn't going to work. These are just some equations about effect size and power. Here's the independent measures analysis of variance, what we called the one-way ANOVA. And here you can see, although there's nothing listed specifically about means, but we need to remind ourselves, why did we do the ANOVA? We did an ANOVA when we had more than 2 groups to compare. So hopefully you remember some of that basic information. That's just some of the key stuff that I expect you to know. But there are ways to verify that you're on the right track. You might be thinking to yourself, I think ANOVA is correct, but how do I know for sure? Well, let's just look at some of the formulas. We're going to need t-values, totals for each group, a grand total. We have small n's and big N's. Let's go back and look at that example. Even in this example, you can see some of the notation that's used fits the ANOVA formulas. We see t-values, totals for each group. We see small n's, the number of people in each group. We see the large N, that's the number of people overall across the 3 groups. Do you see how this example fits our basic understanding of analysis of variance, and it also fits the formulas that we need to use? That's how we know the most appropriate test for this situation is the one-way analysis of variance. Let's give another one a try. This one right here says, an education psychologist administered an optimism test to graduating college seniors. Higher scores reflect more optimism about their future. At this point, that information really means nothing to me. It helps put the particular test in perspective. It helps to give some background information, but really right now, it offers no key information for determining which test is most appropriate. It says last year's class had a mean score of 56. All right, I see a population mean. I'm clearly going to compare something to that population mean. So I might highlight mu equals 56. It says a sample of 25 seniors from this year's class produced an average score of 59. I see a sample and I see one sample mean listed right there. So already I can tell this is going to be a one sample test. Along with that sample mean, I see a sample standard deviation right here. So I'm going to make note of that. Based on the sample data, can the psychologist conclude that this year's class is more optimistic than last year's class? So clearly I'm going to compare this sample mean with this population mean. Let's look at our formulas and see which fits most appropriately. So I'm going to scroll back up. You might recall that the first two tests we were looking at before are both one sample tests. I see one sample mean listed right here compared to a population mean, and one sample mean right here compared to a population mean. So far, those two tests are looking like they could be appropriate. For the z-test, I need to compute standard error of the mean, and here's the formula for standard error of the mean. I need to know sigma, right there, the population standard deviation. I was not given that information in that particular example. For the one sample t-test, I need to compute estimated standard error of the mean. And here's the formula for estimated standard error of the mean. It's based on the sample standard deviation. I do have that information. So do you see how all the information we have in that example fits this formula right here? So like I said before, don't overthink it. If the data fits the formula, then this must be the most appropriate test. So the answer to this particular example is a one sample t-test. Let's look at another one. This one says, in a study of jury behavior, two groups of subjects. So already I feel like I'm being given important information. So underline that information. Two groups of subjects were given details about a trial in which the defendant was obviously guilty. Both groups received the same information, but group one was also given some evidence that had been withheld from the original jury by the judge. Both groups of subjects deliberated and recommended jail sentences. Is there a significant difference between each group's sentence? Sample size equals 8 for both groups, and then we see a mean for the first group, and we see a measurement of variability along with that first group, sum of squares. We see a mean for the second group, and we see a measurement of variability along with that second group. So it looks like the first group gave a heavier sentence, a harsher sentence than the second group did. All right, the details don't really matter. What I'm seeing here is that I collected data from two different groups, and I have two different sample means that clearly I'm going to want to compare. So let's see if the information matches up with one of the statistical tests that we're familiar with. So we need to consult our formula sheet. All right, we know that this is a two sample test, and this one right here is a one sample test, and this is a one sample test. They both have one sample mean. So I'm going to scroll down just a little bit. Right here I see a t-test, and I see one sample mean listed, and it's comparing that to a second sample mean. That's starting to look pretty good. It's looking like that might fit. You might recall that when we learned this particular test, this value right here is always based on the null hypothesis. And the null hypothesis would be there's no difference between the two populations. So we know that this is always going to equal 0. Let's just continue to look at this formula and see if we have all the information that we need. We know that we would need two sample means, and we know that we have that information. We would also need to compute the standard error of the difference between the means. Let's look at that formula. This formula is based on pooled variance and also based on the sample size for each sample. We know how many people were in each sample. That information was provided to us. How could we compute pooled variance? Let's look at the formula for pooled variance. In order to compute pooled variance, we would need to know sum of squares for each group, and we do have that information. We would also need to compute degrees of freedom for each group, and we could easily compute that because we know degrees of freedom is based on the sample size, and we know the sample size. So do you see how it fits? All the information that we would need to compute that particular test right there, that's an independent samples t-test, all the information that we would need is in the summary regarding the particular research study. So in this particular situation, the appropriate test is the independent samples t-test. I hope you're starting to get the hang of this. Let's go ahead and look at another one. This says, examine the following data. Is there evidence that the two variables are related in the population? Well, here it says two variables related. So I'm already starting to think This probably has something to do with correlation and regression. It was during correlation and regression that we talked about measuring people on two different variables and seeing if they might be related. It says test using a two-tailed test with an alpha of 0.01. None of that matters right there in terms of picking the most appropriate test. Then compute the slope and y-intercept so that you can obtain the best fitting straight line for these data. My friends, you've got to know we're talking about correlation and regression right here. It was only when we were talking about regression that we were talking about fitting the most appropriate straight line to our data. We are given raw data, so let's just go ahead and look at the formulas for correlation and regression and see if it would match, see if we'd be able to compute all the things that we need based on that raw data. So I'm going to scroll down just a little bit more here, past the formulas for analysis of variance, and here I've got some formulas for correlation and regression. So in order to compute that correlation coefficient, I need to know the sum of the products of the deviation scores and also the sum of squares for the x variable and the sum of squares for the y variable. Already it's starting to feel to me that it fits because here I see references to an x variable and a y variable. In other words, it's making references to two different variables, and we know we have data from two different variables. In order to compute the sum of the products, I need various sums, and I can get those sums from the two different variables that I have. In order to compute regression, I would need to know the following information right here. In order to compute the slope, I would need to know the sum of the products, and I need to compute that for correlation. In order to compute the slope, I would need the sum of squares for the x variable. I have a formula for sum of squares on this formula sheet. We could do that for the x variable. So again, you can see that the data we have that comes from two different variables fits this situation well. This is going to be the only set of formulas we see that refers to an x and a y variable. So don't overthink it, my friends. It doesn't really even matter what those two variables are. When we know there are two variables and we see that we're trying to figure out how they're related, and then we're going to try to fit a line to that data, we're talking about correlation and regression. There is only one place you should be looking in that situation. So the answer to this particular item right here would be correlation and regression. Speaking of correlation, you might recall that when we discussed the Pearson correlation, we also discussed some popular alternatives that exist, like the Spearman's correlation or the point by serial correlation, and I showed you a table that helps you determine when each is most appropriate. So at some point, you might want to pull out that table and give it another look. Let's take a look at another one. Let's look at this one right here. Again, I'm already seeing three different groups that are being compared. I'm seeing three different means. I know this has got to be an analysis of variance. I'm seeing t-values listed. I'm seeing sum of squares for each group. I'm seeing a g-value, the overall grand total. Do you see how that once you know what to look for, you don't even need to know the background information? Once you just see how the data is set up and how much information you have, you can already start to get a sense of which statistical test is most appropriate. So let's just go back to our formula sheet and verify. So I'm going to go ahead and scroll up a little bit. Here are my formulas for the one-way ANOVA. I need t-values, g-values, small n, big N. I need sum of squares for each group. I have all that information right here in this example. It fits. If it fits, the one-way ANOVA must be the most appropriate test. Let's do one more. Take a look at this one right here. It looks like I have two groups of data, and then I see these D scores. You should already be thinking to yourself, well, when am I ever computing D scores? What are D scores? We're talking about difference scores. Let's read and see if we can get some more information. It says a medical researcher believes that stress increases the symptoms of asthma, so she decides to test if relaxation training might reduce the amount of medication required by asthma sufferers. A sample of 5 patients is selected. During the week before and after treatment, okay, that's some important information. Even though I collected data just from one sample, I collected data from each person twice. There is only one situation that we learned where we collected data from people twice. And now it's all starting to make sense. Because even though I collected data from this person at time 1 and from that same person at time 2, The data that we are actually analyzing is how much they changed. In other words, their difference score. So I'm going to go back to my formula sheet and I'm going to look around and see where is there information about analyzing difference scores. And when you start looking at these formulas, you can see the only formula that we're going to find with a mean difference score is right here. So now we just need to kind of talk ourselves through it. I'm going to need a mean difference score. Can I compute that? Well, yes, I can compute the difference scores and then compute a mean difference score. So yes, I can get that information. I'm going to need to know the population mean difference score. This is where you need to keep in mind some of the basic information we learned. Remember, that value is always based on the null hypothesis. So I always know that this value is going to equal 0. The other thing that I'm going to need is the standard error of the mean difference score. Here's a formula for that. I would need the standard deviation of the difference scores. Here's my raw data. Could I compute a standard deviation of those difference scores? Of course I could. Of course I could. So in other words, I have all the information that I would need to compute that test. So the answer to this particular example is a related samples t-test. I hope you're starting to understand how this strategy can really work well. Just simply look at the information you're provided and then match that information with the formulas that you have on your formula sheet. You can go through the remaining ones on your own if you'd like. On the exam, you're not only going to be given examples like this to compute, but there's also going to be one section on the exam specifically dedicated to questions about test selection. And in fact, that section will be worth 10 points. So there will be 5 questions, each question worth 2 points. And those questions will be multiple choice, kind of like these 3 examples right here. So you'll be asked to read the example, look through it, see what information is there, and then pick the most appropriate test. If you have questions lingering about being able to select the most appropriate statistical test, just make sure you let me know, let the tutors know. Just because you're at a distance, it doesn't mean you can't study together with someone in the class. You can get together via Zoom or Teams or Skype, whatever it might be. But just make sure if you're confused about something, you talk it out with someone. Next week, it'll be final exam week. I'll give you much more information about that exam via email. Most of our exams, all of our exams actually, have been worth 50 points. This particular exam, our final exam, will be worth 70 points. 40 points will be dedicated to new material. Since our last exam, we covered correlation, we covered regression, and we covered the chi-square test of independence. 20 points of the exam will be comprehensive. And what that means is I can ask you questions about things that we've learned earlier on in the semester. The good news is the things we learned early on in the semester, we still talk about now in the semester. Even today, we are talking about sample means and sum of squares. These were things that we learned weeks and weeks and weeks ago. So we never put that stuff away. It still should be relatively fresh in our minds. And then I mentioned to you previously that there's going to be a 10-point section specifically about test selection, and that will be multiple choice. So that would equal 70 points overall. As you're studying, if you have questions about anything, of course, just let me know or let one of the tutors know. Thanks, everybody. I'll talk to you soon.